Okay, good afternoon, everyone. My name is Caroline Oudman. I'm an associate professor in the Physics and Astronomy department at the University of the Western Cape. And it's my absolute pleasure to welcome you today to this webinar that is presented by SciFest Africa in partnership with the Embassy of Spain and the Society of Spanish Researchers in South Africa. And before I present our speaker today, I would just like to ask you, if you have any questions, to please make use of the Q&A tab at the bottom of the Zoom window. So today we have the privilege of listening to Prof Nico Orce. Prof Orsay is a nuclear physicist whose passions are quality science, but also transformation. Nico's research mainly involves fundamental and applied nuclear physics, but also astronomy and mathematical modeling. So with this broad interest, he's explored the nuclear chart, so all possible nuclear isotopes using a wide variety of nuclear techniques and theoretical calculations. And he's discovered new type of collective excitations and shell phenomena in nuclei, so what happens in the heart of atoms. Nico is a leading scientist in research proposals at different laboratories around the world and observatories, and he has secured research funding worth over 50 million rand. He's the leading investigator and spokesperson of the Untitled Spectrometer based in South Africa. He's chair of Taste of Nuclear Physics. He's a referee for most nuclear physics journal, and he's an honorary visiting professor at the University of York. He has graduated 20 master's student and PhD students with research projects generally approved by international committees. His students have traveled the world to gain hands-on experience, present at international conferences, and run their own experiments on world-class facilities such as CERN in Switzerland. And they have led publications in top international journals. So it's with great pleasure that I hand it over to you, Prof. Nico. Thank you.
Thank you so much, Carolina, for the nice introduction. To everyone who invited me, the Association of Spanish Scientists, Spanish Embassy, and obviously SciFest 2021. This is the 25th anniversary of the Science Festival in Africa. I am very proud to be part of it. So let's start the presentation, and the title, as you all know, is Elemental Patterns, or why do we see the same amounts of gold, platinum, silver, wherever we look in our universe. So we see the same amounts of gold, silver, platinum, and other elements wherever we look in our universe through a collaboration of South African and Indian scientists. We may have uncovered one of the hidden secrets of nature, which is why do we see such a universal pattern of elemental abundances, which up to now was not understood. The answer is provided by the subtle interplay between the micro and the macrocosmos, which results, as we will explain, in a narrower nuclear landscape than expected. And before we go into this nice field trip, where we have on the left side here, you have the nuclear chart with all the elements. These are the black squares here. We will see them we'll zoom in a little bit later, are the stable nuclei. And all these are the red ones are the unstable nuclei, many thousands. And these are some of the predictions of how far you can go into that land of terra incognita. And we're going to relate the trip to our different N1s, N2s, our national highways in South Africa, because that's the way I see that everyone can understand what is happening. Or this yellow path here is a reaction network of different nuclear reactions happening. Here you have the reaction network for the R process, where you capture neutrons, and eventually every nucleus wants to go to the stable nuclei, following the principle of minimum energy. And eventually, depending on what they can do, they eventually go back to the black squares here. but we'll explain this in detail as we go through. But before that, I would like to comment on the news of the day and the Spanish scientists in South Africa. They have released a press release about supporting KZN, the University of KZN, and the South African scientists, which uncovered the Omicron variant. And as you know, we got rewarded with a travel ban by most of the European countries and North America. And as you can see here, this variant was already in many countries before it was even discovered by South Africa. So South Africa was penalized by doing a great discovery, which is part of the prejudice that Africa still has, and it's a long battle that we are hopefully winning, but it's a very difficult war to win. You know, to change history is very, very complicated. So again, this recently France has removed the South African ban from South Africa from the red list. Still, there will be drastic restrictions, but this is a continuous effort by everyone, not only the South African, the Spanish scientists in South Africa, but obviously by the presidency, by everyone who is South African is supporting the end of this ban, because that will actually influence the economy substantially during Christmas time. So now we go back, and this was an article which I wrote in 2016 about Africa's universities can track of history and stage science revolutions. And this is what we are aiming, and something has happened since. And this is part of the story that we're going to tell today. So again, breaking history is our goal. Breaking history has to be done solidly and seriously. So this is a summary of what we have been doing lately. It's been published in Nature Physics. Here is the link. And as you can read from the beginning, the abstract, the title is Young African Universities Take the Lead, having long played the role of collaborators with other more renowned institutions. Historically disadvantaged South African universities are now challenging the status quo and emerging as leaders. And this was actually to motivate that little boy and that little girl who was very disappointed. We went to different high schools, and we gave different presentations. It was the International Year of Light. And then we asked at the end to the learners, and then whether they're going to come to UWC, to the University of the Western Cape, to do physics. And then this little boy stood up and said, I have him here. I'm very disappointed with UWC. I will go to UCT. So this is the typical prejudice that it doesn't only exist in the Western Europe and North America, but also within the country, within South Africa. And this is a stigma and the prejudice that we need to break somehow, for everyone to be proud to go to anywhere, and knowing that even if you go anywhere, to whatever university, you can fulfill your dreams. So these are actually some of the pictures. And I remember was one of these guys here, or this little boy here. I think this was the one who actually stood up very sternly and said, I'm very disappointed, I go to UCT. So our goal for this presentation and for the work that we do here in South Africa is to make this little boy and little girl eventually proud to do science and proud of what we are, or where we are. So as in Tsonga, this is they say Sondiri Muronga told me this Mintiro ya vula vula, which means deed speak, right? And we can go and talk about transformation, about all these things, but without deeds, it's very difficult that this little boy will actually believe you. You know, if you just talk to him, he must come with real facts, real deeds, right? So in such a way, we have opened together with South African pioneers, like in this case, Krish Barutram. He was running experiments at CERN before we went there, but ours was the first African-led experiment proposed at CERN, which was led by a South African institution, UWC. And that led, together with Krish Barutram, to open the doors of CERN for any South African scientist to lead science at the big facility in Switzerland. And there's a beautiful, they call it the Ubuntu experiment. And there's a beautiful video that you can see in our webpage here at nuclear.uwc.ac.za. We have brought you the best researchers, the best scientists in the world through the taste of nuclear physics. We have built multi-million facilities here at the Temba Labs. We have built nuclear laboratories at the University of the Western Cape and at the University of Zululand, where students can be trained with the state-of-the-art equipment. And here is some of the students at Unisulu the other day, setting up some of the practicals that we want to do for the third years. Also, we have an exchange program where our students are trained at the University of York on particle detectors in particular. And obviously, here is this famous picture with 13 South African scientists running an experiment at CERN. You know, all of them, they have a South African institution, and mostly UWC students, where we ran many times along in the evenings and at night. So this was the deeds. This is the recent picture was taken last week, where we have a collaboration with the Science and Technology Facilities Council in the UK, University of York, University of Zululand, and UWC, where we are building 2 laboratories, 2 modern African nuclear detector laboratories, again for Mentiroja Vula Vula, you know, for deed speak, and we want to train them as good as we can. But for that, we need to spend in manpower and infrastructure. And this is the ultimate goal, is for you, as Carolina says before, to publish in top journals, but also to give talks at CERN. For instance, here you see Kenzo Abrahams. Kenzo Abrahams is here, who is the famous picture of the Nature Physics. He is from Coles River, and he is giving a presentation next Tuesday, 14th of December, on the Coulomb excitation of germanium-66, which was actually the experiment that we ran at High Isolde at CERN, right? I'm also there giving another presentation, actually, related to the talk I'm giving today, but a little bit more sophisticated. Today is more introduction and trying to explain to everyone, more to the general public. And now we can go through we are taking a deviation through that national highway. We went to the garage, took some petrol, but now we want to address the question, one of the 11 greatest unanswered questions in physics. And the third question was in this the Discover journal, was how were the elements from iron to the uranium made? So resolution, as is written in the journal, resolution of these profound questions could unlock the secrets of existence and deliver a new age of science within several decades, right? So this is the question that we are trying to answer. How were the elements from iron to uranium made? Or at least add more information to what is happening. This is the typical abundance of chemical elements, as where you can see clearly here. Actually, let me just take this spotlight. Here we go. What spotlight? Yeah, here we go. Okay, close now. No, didn't work. All right, here we go. As you can see, hydrogen is the top element in our universe. It was created during the Big Bang, a little bit of helium, and they say a little bit of lithium and beryllium during the Big Bang. And after a few seconds, after 3 minutes, some of the seed nuclei were already produced through fusion, and eventually, you know, you can reach through fusion up to this guy, iron. But after iron, there's no more fusion. I will go through Einstein's formula in a little bit. But the beauty of this relative abundance of the chemical elements in the solar system is stated by Victor Weisskopf, that he mentioned that the composition of matter as we see it today is the product of nuclear reactions, which have taken place a long time ago in the stars or in star explosions. where conditions prevail, which we simulate in our very microscopic way within our accelerator machines. Hence, the material basis of the world in which we live is a product of the laws of nuclear physics. So we go through this in due time during the presentation. So the content of the universe today, as many of you know, we have atoms are only about 4 or 5% of what we see. Then we have 72% of dark energy, 23% of dark matter. And you here have the picture of the W map, where you have these wrinkles in time, which provide information about the age of the universe, about the different compositions that we see, about dark energy being 72%, dark matter being 23% by comparing with different models. And this is a W map, the Wilkinson microwave asymmetry probe, which has taken a very nice picture. Here you can see the picture of the universe, different temperatures, and how this is very nicely written in this book. Not the W map, but the beginning of the Kobe probe, which was worked out by George Smoot, who also came to South Africa to Ames a few years back. Is one of those heroes, you know, those of very, very strong, hard-working people who actually partly made this happen. As you can see, Stephen Hawking said that this scientific discovery, this is scientific discovery of the century, if not of all time, right? So this is a very nice book. I recommend to everyone to read through this Christmas vacation. And I have to remove this because I don't see this thing. Here we go. Accelerating expansion, 72% of is dark energy after the Big Bang. Now we see that some billion years ago, the universe keeps accelerating, which was actually surprising. And this is the way it accelerates. It's probably like people look like, show it like a balloon. When you inflate a balloon, but when you inflate a balloon, these things also, the galaxies and the stars also get bigger. So this remain the same in this accelerating balloon. And you see that the whole universe expands, and this is the only reason that this can happen is by introducing an energy which no one knows about it, and they call it dark energy, right? So this is the consequence of having a universe which is accelerating. There's also the other option, the philosophical option of the balloon, that knowledge is the air inside the balloon, and the more you know that you don't know. That was Aristotle, but my father-in-law keeps reminding me that every time. And we have dark matter, as you can see here. You can see here, this is the typical thing that you throw the coin, right? And there's one at the Zico Museum. I recommend you to go to the Zico Museum as well. And then you throw the coin and then it goes slowly until it keeps speeding up, and it goes very fast as it gets closer to the center, right? This is what you expect according to gravitation. There's a black hole in the middle of the galaxy. Anything which is closer, like happened with the sun and Mercury and the planets, anything closer to the center, to that central force, the origin of that central force, it will go very fast. And if you are far away, you will go slowly around the galaxy, slowly around the sun. But this is not what is happening. We see that at the spiral arms of the galaxy, things are also moving very fast. The stars are moving fast, and the same thing happened with galaxies, cluster of galaxies, where the farther away galaxy is also moving very fast. And the only thing that we can explain this without any is again imagining some extra mass which is affecting the is influencing the gravitational force on these particular objects, where they should go, they should go very slowly, but this is not what is happening. So the faster motion unexpected for stars and the spiral arms of galaxies, implies that we have, out of that 123% is dark matter. Again, we don't know about it. There's a lot of research obviously being done. And so we go to our talk today within that 4%. we are only interested in that 0.05% of elements heavier than iron. You know, within the 4% of the total energy, total mass in our universe, we are only interested in understanding how gold, you know, for many people, gold will be very important. So that 0.05%, even if it's a small number, is probably relevant for the global economy of the world. So this is what you see in the universe: 73.9% of hydrogen, 24% of helium. Our sun keeps burning hydrogen and will remain doing so until, you know, for another 5 billion years. And we see the similar composition in the universe as we see in the sun photosphere. And there's a nice paper, they call it the alpha beta gamma or alpha beta gamma, the origin of chemical elements. That was the first, 1948. Although Bete has nothing to do with that paper, he was put there just to make fun of just to make a sound co-authorship, the alpha beta gamma. And sometimes we see that we have the typical periodic table, and we see some elements according to relative abundance, but this is clearly wrong. You see this in the web page. The same thing I tell my students: don't Google questions, because normally, even in Google, some of the topics are not well explained. In truly, what happens is that carbon was emitted due to the solar heat in our planet and Mars and Venus. All the planets close to the sun. Solar heat during planet formation drove most volatile compounds into space. For example, hydrocarbons, except oxygen, which is found on the silicate materials. 90% of Earth crust. That's why silicon is very abundant. Oxygen as well, aluminum, iron. You know, all these elements are not produced in our sun, but they were produced before in a stellar explosion. Probably there was a supermassive star where our sun lies right now, and the creation of those elements happen, unlike the gas planets where they have similar abundances to our sun and to the universe. Jupiter, for instance, has 74% of hydrogen and 24% of helium, right? So don't get confused. This is a general pattern, and what we see on Earth in different inner planets is the result of solar heat during formation. And so again, we can see the periodic table, and we know how these guys are created, and they are created as such because of Einstein's formula, E_mc squared. After that, these other elements in the periodic table are produced through different ways of neutron capture. So this was the Dmitry Mendeleev. And if you go to Dubna, some of our students go to Dubna, I recommend you go to the Tretyakov Gallery in Moscow and look at this famous painting. As he arranged according to the atomic weights, exhibit an evident periodicity of properties, the elements. And this was what we want to find also for nuclei and for how elements are created, any kind of periodicity, any kind of general property. So I was thinking to prepare this talk for more basic, and then I wanted to introduce the hydrogen atom and how Niels Bohr, remember the story, Niels Bohr just using the fact that the angular momentum is quantized, and just using the centrifugal and centripetal energy, in this case the Coulomb force, the Coulomb attraction of the nucleus to the electrons, right? So he just determined the energy spectral lines of hydrogen, which was, as Einstein said, the highest form of musicality in the sphere of thought. Each element isotope has its own fingerprint, and this is done through spectroscopy. You have a hot source, you can see it goes through a cloud of cool hydrogen gas, and light gets, certain absorption lines that you can see here. And basically, it comes as a dark lines in the typical light. You know that light is, as it goes through a prism, you get the typical rainbow colors. But in that rainbow colors, you have these typical absorption spectrum, which is when you have, for instance, something in between. And this is the way, actually, these nuclear reactions happen at the center of our sun, right? The center of the stars. So in the process when the radiation comes out, there will be absorption lines on the surface of the sun, and these spectral lines are all helium, which means sun in Greek, and it's because they were discovered, these lines, in the sun for the first time. They were not discovered on Earth, and you have here the typical hydrogen lines, all of these, and you can see this from the Orion Nebula. Spectroscopy is a very important tool for us to determine, is the main tool for us to determine the chemical composition of the universe. This is another beautiful book, Autobiographical Notes by Albert Einstein, and that this insecure and contradictory foundation was sufficient to enable Bohr to discover the principal laws of the spectral lines and of the electron shells of the atoms appears to me a miracle, and appears to me a miracle even today. So, as I tell my students, this was not the end of the story. He got the eigenvalues, but later on we had to get the eigenfunctions as well and apply the big Schrödinger equation, which provides all the information about the quantum system. But this was at that time worth of a Nobel Prize, and that was awarded to Niels Bohr. Also, we have our cartoons about Niels Bohr. If you go to the taste of nuclear physics, you have lots of cartoons, and we try to make cartoons also for our students to get the concepts in an easier way. You can see some of the cartoons here at the taste of nuclear physics. Here we infer that Niels Bohr was quite a tough cookie, and he was always a little bit too enforcing the rules of quantum mechanics to everyone. So Einstein wasn't very happy to see him all the time. So here is the nuclear landscape. As I mentioned at the beginning, the black squares are the stable nuclei. This is the terra incognita, far away. How far away you can go is still a mystery. And this is one of the questions that we're going to try to answer today. This is called the neutron drip line. After this, nuclei are unstable and they emit a particle. They are unbound, basically. And that's why this is called the neutron drip line. And there's a proton drip line also on this side. And as you can see here, these are the known nuclei, stable nuclei. And there are many thousands of nuclei that we actually don't know. There are 300 stable and several thousand of unstable nuclei. This is again a nuclear chart and then I want to actually, once we are here, I want to show you this. This is a 3D nuclear chart of what a more detailed one. But you can go around and see, you have all the isotopes, and you can click on any of the isotopes and get information about any nucleus that you want. You see the black squares are the stable nuclei and how they are produced. You go, this guy capture a neutron, capture a neutron, capture a neutron, capture a neutron, until capturing a neutron is not providing, is not an exothermic reaction anymore, and it prefers to go beta decay, beta decay, beta decay, beta decay, and go here, right? So these are how things are happening in our universe through these stellar explosions of neutron star mergers or whatever, And the fact of the matter is that we don't know how far this goes, but maybe now it's a good time maybe to show the movie of how these elements are produced. Is that okay?
Sure.
Yeah, let me stop sharing for a sec. You see here we have, as I was saying, we have the typical neutron star mergers, of supernova explosion, and you can see how the elements. This is a prediction. It's not what really happens, because what really happens is still unknown. We don't have enough observations. These are calculations of what happens according to the laws of nuclear physics, as we know today. they are produced. The elements capture neutrons. They go far away into the neutron drip line, and eventually everyone comes to the valley of stability. Everyone comes to the sofa to watch some soccer and don't do anything for the rest of the day. So you get a lot of activation and stable nuclei. Eventually, you go to the stable ones where you just relax, right? Thank you very much for the video. That's one of the paths that supposedly is called the rapid neutron process. Let me just go. Here we go. In show from current slide. All right, we continue. And again, this was an introduction. I was thinking that this will be for everyone, a talk for everyone to learn a little bit of nuclear physics. And this is how the nucleus was discovered. Remember that you can shoot an alpha particle into this layer. You can shoot a bullet through a piece of paper, a sheet of paper. And what was surprising is that bullet came back. It backscatter, as we call it. And this is the reflection. As you can see, these pinky reflections here were totally unexpected, because as you can see, the nucleus was supposed to be this sheet of paper where the bullet can go through the alpha particle, and most of them are expected at these forward angles without being deflected. And but this guy, Marsden and Geiger, they almost lose the eyesight. They almost went blind, because they had to eventually look at these photographical plates and see when there was a boom, 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 a little bit of flash of light, to see that actually these alpha particles were bouncing back. And no one knew that. And no one knew how to explain it. I was explaining in a way, that there must be something in the center of this atom, and that was the name. That was called the nucleus, right? Nucleus is composed of protons and neutrons, and has most of the mass of the atom is concentrated in that nucleus. So then we have, as we mentioned before, the fusion happens according to Einstein's formula. There's a release of energy, what we call an exothermic reaction. And after iron 156, actually the most bound nucleus is nickel 62, but after iron 56, the reactions you cannot fuse anymore, because then you need to provide energy. The reactions become endothermic. And then this is our endpoint up to iron. These guys can also release energy by fission, but they cannot produce elements through fission. So what happens here is that these seed nuclei, which have been produced in an easier way, say, only through the big explosions of neutron star mergers, and you reach enough temperatures and enough neutrons, right, for those guys to capture neutrons and become something heavier and heavier and heavier, as seen in the movie, basically. So as you can see, stellar fusion of elements up to iron, and after iron, Einstein's formula, delta E equal delta M times C squared, the difference of the masses of those guys who fuse and whatever is coming after. The product, they don't produce any more energy, they don't release any more energy. So the rest are produced by neutron capture, where no Coulomb barrier is involved. So as keeping the introduction, this happens in our sun, the fusion of two protons. We have two protons here and two protons there, and eventually this is the PP chain reaction. Release energy, release energy, release energy, release energy, and this is how the sun emits all this radiation, which leads to life on Earth. There's a beautiful, this is Soho satellite, a picture from the Soho satellite, and you can see these flares coming out, and you can see how this may affect satellites in our planet. And that's why we also have the SANSA, South African National Space Agency, which also deals with this phenomena. And they need to know what's happening. All these flares happening from the sun, a big flare pointing towards us, is generally shielded by the magnetic field, but not entirely. And sometimes you may have electromagnetic pulses which affect the old satellites. So again, this is a way that things happen in the nuclear landscape by nuclear reactions. You can capture a proton, an alpha, and eventually you go, depending on the Q value of the reaction, you go up and down and produce. This is a typical RP process, the rapid proton process, which happens during nova or X-ray burst, a different stellar explosion scenario. And this is eventually what I want to explain, that all these processes, the RP process that we see right now here, the R process that we saw before in the video, there are different paths which can be connected somehow to the national network of highways in South Africa. So these are all produced in different super, stellar explosion, nova, AGB stars, the S process, the X-ray burst, the rapid proton capture process, or neutron mergers or supernova, the R process. Here, we go through what is the S process, slow neutron capture, which is happening in the interior of AGB stars. There are some very strong turbulences, and these turbulences lead to the emission of this matter. But the reaction mechanism is basically you go through here, capture neutron. Oops, you cannot capture more neutrons because there's no more easier. There's not too many neutrons here. The temperatures are not so high. So you go back here. You keep going through the valley of stability through the black squares, and then you produce all these elements, right? And the Geiger satellite is in charge of looking at these AGB stars and mass losses. So then, how do we know what is produced by the R process, by the rapid neutron capture? Basically, we know pretty well what is how the elements are produced through the S process, slow neutron capture in AGB stars. Now the remaining must come from the R process. When we don't know too much, we simplify the situation, maybe right, maybe wrong, but these are all the information that goes into the determination of the R process and the abundance of elements is to see what is the actual abundance, what is produced by the S process. The remaining must be coming from the R process. When you don't know much, you make these assumptions, maybe right, maybe wrong. But the thing is that you have here the different calculations for the neutron drip line, and you can see there's a very large variety of calculations. And depending on the different interactions that you use and the different reaction mechanism, the information on reaction rates, the information on nuclear masses or atomic masses. So all this comes into this onto this network calculation, and the video we show is one, but there are other possibilities, actually many possibilities, many predictions for the neutron drip line. So eventually, we have to reach up there to see where it ends, right? Where the terra incognita actually ends. So this is the information that we know for neutron star mergers that as soon as they happen, all the telescopes in the world, including the ones in South Africa, MIRCAT, all they pointed at the neutron merger. They were localized, and then some of the information was that there were some strontium lines, strontium 2 lines, that they are blue shifted because the neutron mergers, depending on whether it's moving away or moving towards you, you will have, if it's moving towards you, it's a blue shift. If it's moving away, it's a red shift. And in this case, this neutron merger seems to have been moving towards us, and the actual line of strontium 2 is here, and it will be blue shifted to the left. And this dent here was associated with these strontium 2 lines. And so elements were actually observed out of this massive explosion of neutron mergers, which was actually quite impressive and amazing, because remember, neutron stars are the gravitational pull is very strong, right? But the energy release is much stronger. And that was a huge discovery. Not only the LIGO, the gravitational waves, but also in terms of this 4% of matter, it was important for us to know where the matter is produced, because no one up to now, until these neutron mergers, happened, neutron star mergers, no one really knew what was the astrophysical side for all these elements to happen. It was supernova, explosions, neutron mergers, collapsars. There were different options, and probably there is a combination of all the options. But until then, no one saw this emission of elements. Again, we go back to the abundance pattern. We measured that through the light coming from different stars, and we see again hydrogen is the top, 70 few percent, 20 few percent, and the rest is much smaller, relatively speaking. But it's very important for us to understand how these guys from iron they are produced, right? All these guys here, we want to explain how they are created. Partly, it's important that we also have SALT and the HRS, which is another flagship in South Africa. In South Africa, we have a lot of beautiful things to be proud of, beautiful instrumentation. We have Itemba Labs, we mentioned. We have the SKA, we mentioned. We have the SANSA, we mentioned. We have the SKA, we have we have SALT. So it's a beautiful country to do physics, to do anything that you want to dream about. I mean, there's not many countries like that, where you can do anything and you have all these big devices, to do state-of-the-art science. So basically, this is the situation. We have the first Big Bang, some population 3 stars. I don't know why they call it population 3, but these are like big supernovae. They are created. Eventually, you have all these AGB stars, the oldest stars in the universe, which are still existing, and they are less than 0.1%. I think it's 0.01% population. And obviously, those stars are very important because when you don't understand clearly what is how elements are created, you want to always go to the simplest case scenario. Right, this is our sun, a lot of absorption lines here, a lot of elements, because it's not the first star there. There was a previous star before, which created all the elements that we see on Earth. And then, as you can see, as you go in lower metallicity, you go to an older star, obviously the situation is much simpler. There's less elements, and then to the oldest, one of the oldest, or one of the most metal poor stars, here, this guy, He 1327, 2326, with a relative abundance with respect to iron of minus 5.6. So you can see that the spectrum is very simple. Only one line here of iron, one, another line. So this provides a lot of information because it's not so complicated, right? Hopefully we can understand the simplest case scenario. And this was the goal of why we went to SALT, to the high resolution spectrograph. And we actually, together with Dave Kilkenny, Tony Lynas-Gray, and a team of students, we have collected data. And I thank all the SALT astronomers for collecting the data for us. And we got some information. We got some information thanks to Dave Kilkenny, who is the top astronomer, and Tony Lynas-Gray, who is the expert on opacities, on how light goes through these stellar atmospheres. We could manage to do some simulation and explain some of the lines that we have in our star, which actually was one of those metal poor stars. So we were a little bit lucky, or very lucky actually, to get one of those 0.01% population. And we look at the photometry. Here you see, I don't have no time to explain why, but all these guys on top here, they are candidates to have low metallicity. And you can see some strontium 2 lines, some barium 2 lines, and the metallicity was -2. We also could see that the radial velocity, how far is moving away from us, is 170 kilometers per second. The surface gravity was simulated and the effective temperature through the different, as I say, different opacity models. And this is the way you get the abundance of elements, right? These are 6 stars, right? In the R process, rich galactic halo, and compared to the solar system abundance distribution, these blue lines, as you can see, all these 6 stars in the halo, in the galactic halo, they present a very similar pattern of abundance. And this is what is called the universality of the abundances of the elements, because you can see that our sun and faraway stars, they present the similar abundance patterns or relative abundances, which was quite surprising. People wonder about this because, as you can see here, it's quite remarkable that you can see everywhere you see in the universe. As long as you can see in the universe, you can see the same pattern. And it was Cagino who mentioned that the elemental abundances of metal poor stars in the galactic halo exhibit the same elemental process abundance pattern as known from the solar system abundances. This pattern appears to be rather universal. However, this fact suggests a rather well-defined origin of heavy elements beyond iron. We do not know if this may be only an artifact of nuclear properties, such as binding energies and beta decay rates, or it may point to a single cosmic site with astrophysical conditions that are generated uniformly throughout cosmic time. So as you can see, 2019, this was a surprise. This was an unknown, how all these stars, how we can see out there, and we see a universal pattern, but there's no way we can see a universal pattern coming out of these calculations, right? Because all these calculations, they were giving you different possibilities, right? You have all these calculations here, different trip lines, right? So the more you open, the more possibilities you have. It's more difficult to predict why suddenly we have a universal pattern. You know, what is happening out there, which makes this abundance trend to be universal. So here we go. So we go back again and see what's happening, because we in nuclear physics, we must understand, you know, we know that these stellar explosions are happening, nuclear reactions are involved, and how this is how elements are created. And independently where you look at, either you look at the neutron star mergers, or you look at supernova or nova explosions here. So all these elements must be produced in a way which follows some of this path, right? The RP process, rapid proton, the rapid neutron, stellar fusion, the proton process, the neutron star process, the supernova core, S process. You know, there's different processes that we have gone through, some of them. And then we will move a little bit to the nuclear physics, and we see that this is a discovery by Arkady Migda in 1945. You know, 1944, actually, at the end of the Second World War, where you can, you know, imagine that still there were scientists trying to uncover secrets of nature. And he predicted what is what's called at that time the giant dipole resonance, which is a motion of protons and neutrons, collective motions as you excite the nucleus, collective motion of proton and neutrons out of phase, right? As you can see here. And this motion characterized pretty much the symmetry energy and characterize the abundance of elements, as we are going to see in a little bit. So this giant dipole resonance of atomic nuclei prediction, discovery, and research, there's a 75th anniversary of that discovery. So as you can see, there was a 50th anniversary of that paper, and here is the latest one, a 75th anniversary of that paper. Arkady Migda was one of the heroes who will be in the history books forever. So the Manus students, the masters in nuclear science students at UWC, we assigned them a little job here, a little project to study the symmetry energy. And I haven't defined the symmetry energy because I didn't want to go into too much of mathematics, but they figured out that it converges to between 23 and 27 MeV. And not only we have these GDRs built on ground state, but also we have these GDRs built on excited states according to the Brink hypothesis. And this allows us to study these properties as temperature goes up, as excitation energy goes up, which is actually the case for these explosions, stellar explosions, right? Most of the information that we know is for the ground state, but during those explosions, nothing is at the ground state. temperatures are less than 1 MeV. You start with 10 to the 11, actually 10 to the 12, going back quickly, very fast. As you can see this, you can read this book pretty fast. Things go down to the creation of protons and neutrons and the formation of low mass nuclei. These are the seed nuclei, and this is what's happening in the neutron star mergers. You have a kilonova, this huge energy being released at 10 to the 12, 10 to the 11 Kelvin. It's also different gamma ray bursts is happening. Then you have quarks and gluons. No matter has been created yet in terms of proton and neutrons. Then these are produced. Again, this is the first 3 minutes after the Big Bang, but some of the processes are similar, right? As this Big Bang is happening at much higher energies and temperature, but the quark gluon plasma is also happening in the kilonova explosion, and eventually proton and neutron formation of low mass nuclei. And these seed nuclei are the ones which eventually these seed elements are created before charge reactions freeze out. And then at these temperatures, less than 0.5 MeV, these seed nuclei start capturing neutrons and they start producing those elements heavier than iron, right? So at few 10 to the 8 Kelvin, neutrons are finally consumed and the whole process finalized as we saw in the movie, right? So here, actually, here's the binding energy, and you have the symmetry term here. And as you change, we realize that the symmetry energy for these high temperatures, at those temperatures similar to the stellar explosions, the temperatures in those stellar environments, like neutron star mergers, 10 to the temperature of 0.7, 0.1 MeV, which is about 10 to the 9 Kelvin. So we realize, we determine from experimental work on that GDR, giant dipole resonance, that the symmetry energy actually changed from whatever is known in the atomic mass evaluation to 20 or 16, but also if we can show you here quickly. If we run this, this is a simulation. Here we go. This 23 MeV for the symmetry energy. We run this. We have a binding energy like that. Atomic mass evaluation. This one is the 2020. We are comparing with, and with this symmetry energy, we can reproduce nicely the trend, the experimental trend given by the atomic mass evaluation. This is the same empirical formula by Bethe Weizsäcker. If we change this to something higher, then Control S, then we see that the situation becomes a little bit more complicated, and you can see that the binding energy actually drops quite substantially as compared with the masses, and these masses obviously are masses of the ground state. As you increase the temperature, the nucleus loses binding energy and loses mass in the way that that you drop the binding energy per nucleon. Same thing, we can use it for the let me see here, for the Python chart. Let me see what I got here. This for 23 MeV. As you can see here, what's happening? You have a big nuclear shard. This is the nuclear shard that we see in the plots below, which I showed before. But again, we change the symmetry energy to something higher. You can see that this guy actually decreases, right? And you can see how this very broad becomes much thinner. So basically, the nuclear shard, the terra incognita that we are talking about, is not so broad, so widespread, but the whole thing narrows down in a way, and this is our claim, in a way that things become universal, because as you don't have so many probabilities, so much of game for the R process to evolve, you are narrowing down the possibilities because the binding energy are decreasing and also the reaction rates are decreasing substantially. So now let's go here. Let's go back, and I'm almost done. right? So as I say, we change the symmetry energy at high temperatures. Actually, it should be 0.7 to 1 MeV. This was the calculation I just did right now for you guys, where you can see a much broader neutron drip line here than here, as the symmetry energy increases with temperature. This was the experimental finding, right? So again, what does this all mean? That the roadmap or the highways are well defined. You know, you are producing these elements, and you don't go too far off in that terra incognita that we saw here. Let me see if there's a nice, actually this one here, all these are known nuclei. That's a nice one here. All these are known nuclei. You don't go too far off, which in a simile with our national road system means that if you take then one to Joburg, you go to Joburg, but you don't deviate. You can deviate maybe to take some petrol, but you don't go to Durban if you take the N1, right? So this is the way things happen. There's a particular process which, in this case, all this movie that we saw before, the neutron capture doesn't reach so far off, and that's why if you narrow down the nuclear chart, this implies that the process, the R process in this particular case, narrows down and things become more universal. There's not so many possibilities, right? So this is the claim that we are making, basically, that the N1 goes to Joburg but not to Durban, and this is the simile in this particular case. I hope I have explained this very important point, because these explain the universal pattern of R process abundances observed in galactic halo nuclei, or actually in galactic halo stars and our sun. And these high temperatures, there's a clear closing neutron drip line which constrains the R process flow and narrows down the nucleosynthesis of elements, right? This was submitted to Physics Letters B, and now we are going through the referee process. We got the referee report, and we are going to work on those suggestions. And this is part of the South African or the India-South Africa collaboration. And these are Andile, I think Andile Zulu is missing here, but these are the members of this collaboration. And I'd like to thank the SciFest Africa, of course. This is the symbol of the nuclear warriors. I don't know if I mentioned that. This is the Association of Spanish Scientists, UWC, University of the Free State, NIFEX, the National Institute for Theoretical and Computational Sciences, and obviously the Spanish Embassy, that they all sponsor this event. And I want to finalize saying that this process is a hard process. This route, this field tree that we made, requires a lot of effort, because you have to combine many different fields, right? And this can only be done if you have the science motto that is stated in this beautiful book, Monday starts on Saturday. And they had accepted as a working hypothesis that happiness lies in the constant cognition of the unknown, which is also the meaning of life. Thank you very much. Here you go.
Thank you very much, Nico, for that great presentation. So I would like to encourage anybody who has questions to post them in the Q&A, and then we'll be able to pick them up from there. I have a couple of questions. So I think what is quite extraordinary in this research is that you seem to be able to demonstrate that there are only certain ways that elements can be formed, knowing what's happening in stars and in neutron star and different types of stars, and that you're able to confirm that with theoretical calculations. Have you tested this in accelerators and in the lab as well?
Actually, this is a point which I failed to explain well, I failed to explain well because I removed some of the slides to make it simpler. But all this doesn't come from observations. From observations, we see we see that there's a universal pattern, right? But all the things that we are deducing come from nuclear physics experiments, right? From the study of the giant dipole resonance and how these giant dipole resonance change in magnitude as you go up in temperature. So these are all information obtained from nuclear accelerators. Some of the papers from our Indian colleagues, and some other papers we collected all the information which was available for these high temperatures, which are in the same range of these explosive scenarios. But basically, all the information coming out of here comes from the GDR, the giant dipole resonance, and how this effect changes at high temperatures.
Okay,
I didn't want to go
so
too much. Yeah.
No, but that helps clarify already a lot. I see there's a comment here from Christine Stenkamp, who says, thanks, Nico, for the inspiring talk on how the nuclear physics helps to understand the universe. So there's a compliment there for you.
Thank you, Christine. Thank you very much.
I have another question for you. This is more of a speculatory question. So you showed us in the beginning that most of matter in the universe is made out of dark matter. What are your thoughts on what dark matter is, and do you have any thoughts on how that could be tested?
This is, I will answer with that course that you want to introduce for the honor students. It's the same answer. You know, if we don't know what is the matter that we see, if we don't see the 4%, we don't understand. I don't want to know what happened with the 23%. Let's first do the core subject, you know, the difficulty ones, you know, and then we move forward and do your beautiful course that you want to propose or you want to do for the honor students. So basically, for me, it's the same approach. I don't care about dark matter as much as I care to understand that 4% of matter that we see around us, you know. Although it's very relevant, it's very important, I believe in it, but I like to understand what we see, you know. Because the other one is more difficult, you know. It's more difficult there's a lot of varieties, you know. I have enough of possibilities, you know. So I want to focus on something that is more, that has more substance, you know.
Mm-hmm. Yeah, no, definitely. So I see another comment here from Lebohang Moropane, who says, very informative session. Thank you, Prof.
Thank you so much for the comment. Actually, if I thought I thought that it was going to be a talk for anyone, and it is so. But if you want, I can have a couple of minutes and explain why, you know, a little bit detail what nuclear information we are extracting for us to make such conclusions, right?
Sure, go ahead.
So I'm going to show you. Let me just quickly, right, because that wasn't clear. I didn't want to make it too complicated with equations and things. So basically, let me see. So these are the equations. They are related to the nuclear polarizability, and this is inversely proportional to how the nucleus polarizes. Obviously, this giant dipole resonance is polarizing the nucleus, and this is a second-order effect in perturbation theory. So the symmetry energy is here in the binding energy curve, right? In the binding energy description of the same empirical mass formula. But then we look at high temperatures. Most of the information here is for ground states. And then we have for T equals 0 MeV, that means ground state nuclei. We have a pattern. But here we go and we look at the nucleus at different temperatures, right? And this is a giant dipole resonance that is typically built on the ground state of nuclei, but it's also built on excited nuclei, excited states of nuclei. So what happens is that this giant dipole resonance, it moves to the left. By moving to the left, by just 3-4%, it moves to the left in a way that, let me explain here. Here we go, this formula here. In a way that this energy, the total for the absorption cross-section from that giant dipole resonance moves to the left, and this sigma minus 2 here gets, as you get a smaller energy here, a square in the denominator, you are integrating between 0 and E gamma max. As you get a smaller energy, this number becomes bigger, and this number becomes bigger. Let me show you. Oh, no, I went too far. Sorry. This number becomes bigger. Here we go. So it does the nuclear polarizability because they are related, right? Alpha is proportional to sigma minus 2. And eventually the symmetry energy becomes the opposite, right? So if sigma minus 2 gets bigger, the symmetry energy becomes smaller. And the symmetry energy actually characterizes the principal, the most fundamental variable of the giant dipole resonance, which brings down the binding energy. You know, that's the whole process. So eventually, we look at this from measuring these giant dipole resonances built on excited states. You know, and we see that the measurement of the symmetry energy doesn't change with temperature, from the range of 0.7 to 1.3. But the main question arising here is what happened below 0.5. We don't know that yet. So the claim that we are making here is a claim assuming that, remember, at 0.5 is when you start getting neutron capture. You know, it's when you start producing those elements. We haven't gone that down. We haven't gone to 0.5 because there was no information there. And this is where experiments using the GAMCA facility at Itemba Labs can help to go down and see. Actually, this is the remaining thing experimentally to see whether this trend holds up down to 0.5 MeV, where the neutron capture starts happening, right? So I didn't want to go through this plots here, but basically you can see here how the symmetry energy changes for ground state nuclei. This is the red curve, and this green curve happens for high temperatures. You know, the ones which are in the stellar explosions where nuclei or elements are created. Okay, so that's I didn't explain that in the presentation because I thought it was a little bit too much, depending on the audience. But if I see that there are many university students and people who know things, so it's better to explain it fully. So there's no discussion. This comes from nuclear experiments, and we are just trying to explain astrophysical observations, right?
Okay, yes, thank you. So it's really interesting to see how with your experiments you link the very small to the very large that's observed.
That's the beauty.
Yeah, it's fantastic. We have two more comments. One from Christina Moniudis, who says, I'm definitely an anyone and thoroughly enjoyed your talk. Thank you, Nico.
Thank you so much. It was, thank you so much. Yeah. That was complicated.
And Ana Manchevo says, very inspiring talk as always. Thanks, Prof Nico. So I think you have a very happy audience today. So well done. I don't see any more questions. If anybody would like to ask a question, I'm quite happy to let anyone raise a hand. But I don't see any hands raised.
Don't be afraid to ask. As I said at the beginning, it took us 2 months to find one referee to go through this paper, you know. So it's not an easy thing to involve, although I think I explained it the simplest way possible. But as you see, there was a lot of nuclear physics which I thought it was going to be complicated.
Yes, exactly. Okay, then I have another question for you. The abundance of stable nuclei that you have in the universe and that on planet Earth is quite different. So you explained early in your talk that a lot of heavy elements have been lost because of the sun wiping them off the planet. But can you say something about the inside of the planet, maybe, because we have an iron core, right? So can you comment what's under the crust?
Yeah, so only the heat, the sun heat, only evaporated those volatile, you know, like carbon compounds. not inside the crust, which is mainly silicon, right? So that remained there, but basically what was outside in the atmosphere, all the gases, all the molecules, and that was kicked out because of the high temperatures. But inside, whatever was inside, nothing it remained the same, right? So, but those extra abundances, that we see of hydrogen, helium, these light gases, they were sent away, they were kicked away by the sun heat, and that's why we don't see so much of hydrogen. That's why we don't see the same kind of 74% of hydrogen, 20% of helium, and we don't even see so much of carbon as we see in the universe, right? We see oxygen, we see silicium. However, when you have the massive planets like Jupiter, Saturn, then again you see the similar pattern as in our sun and the universe, because they were farther away and there was not so much of heat for those volatile compounds to be ejected to kick out outer space.
We are lucky to have kept all the heavier elements that make what our lives possible, right?
Right.
Great. Okay, so we have 2 more questions. One from Ubong Moses Okon, who says, thanks, Prof, for the insightful presentation. Will the recording be made available for participants? I think the organizers have to answer that, but I believe that, yes, they will be available. And another question, which is more technical, from Anton Hartmann, who says, can you comment on symmetry energy in neutron star matter?
So that's also a very, very crucial question, because depending on the symmetry energy, these are part of the synergy between SKA and nuclear physics. It's very important to understand what is the symmetry energy in neutron star matter, but this is done through the equation of a state, and this is a entirely different topic. But the first derivative and the second derivative of the symmetry energy, they affect, and this is one of the goals that we want to make. And let me just actually go through. Can I share the screen quickly, Carolina?
Yes, go ahead.
So here, one of our goals, although it's at normal nuclear densities, and we don't know what will happen at very high neutron star density, but one of our goals, as I've showed it in this review article in World Scientific, it is to determine what is the symmetry energy. This is a sigma -2 for different symmetry energy parameters. This is the volume, and this is the surface to volume parameter. And you can see that different predictions, and this is written also in the proceedings of the 4th South Africa JNR Symposium in Dubna. And you can see that there are different possibilities according to different theories, or different models, and we don't know exactly what trend is happening, right? So this is one of the things that we also want to do with GAMCA. We want to do Coulomb excitation, and Coulomb excitation allows us to determine so far there are only 2 data points here. So that's why we need to do a systematic study of elements of Coulomb excitation of nuclei, basically excite the nucleus through the Coulomb force, right? And where there is no nuclear force being involved, because we don't really know the nuclear force, and see whether we can follow a pattern of this data. Basically this green diamond. This one is high up, so we want to do these ones, and these are being approved as high priority at the Temba Labs. And now we're going to propose 2 experiments at CERN. Sebon Wetseni, our student, will be proposing an experiment in January to run 2 of these exotic nuclei at the high solder facility at CERN. And that proposal has to be accepted and has to be run. And the same thing happened with the proposal at Temba Labs also, although it has high priority. Because of load shedding and because of COVID, we haven't been able to run. And these are the things that we want to study. If there's any trend that we can deduce from Coulomb excitation. I know there are other different experiments done with relativistic protons, polarized protons up here for heavy nuclei and neutron-rich nuclei, where they also study the neutron skiing and other things. but we're interested to know how things change here, because here is where, if I can actually bring it up too much, as you can see here in light nuclei, where things change quite dramatically. But if you go for heavy nuclei, everything kind of converges here, and it's difficult to see which parameters actually are the best out of all these possibilities, right? So these are something else that we want to do at the Temba Labs and at different facilities worldwide, to study the symmetry energy at typical and normal nuclear matter, right? Then do you have to extrapolate that to the actual very high densities in neutron stars? But there are ways of doing so. Okay, I hope I answered the question.
Great, thank you very much. We have one hand raised. Orsay, you can go ahead. Okay, you're still muted.
Orsay, you get five more points. I think Orsay is my student, honor student. If you ask a question, any honor students who ask a question, they get 5 more points.
Okay, I can't seem to. It says talking permitted, but it doesn't seem to unmute you. So maybe if you can type the question if we can't get you to.
Okay. All right. I think, Carolina, if not, I actually need to go and pick up my kids.
Okay, all right. Okay, no problem. Sorry, Orsay, you'll have to ask the question directly to Prof Nico when you get in touch with him. Okay, well, thank you again very much for your presentation. This is a very ambitious topic, and I think it was really appreciated by the audience. Thank you also to SciFest Africa, to the Spanish Embassy, and to the Association of Spanish Researchers in South Africa for making this webinar possible. We hope you all enjoyed, and I guess you have all the contacts for SciFest Africa, and follow for more webinars.
Thank you so much, Carolina, everyone who made this happen.
Okay.
Thank you.
Thank you so much. Okay, bye.